Well, let's talk about properties of logs. Here are some rules that everybody in Math 101 needs to know. The first one, property 0, I gave it the number 0 because it's just the definition of logs. Log base a of x equals y means that x equals a to the y. It means that y is the exponent I raise a to in order to get x. By the way, you can't take logs with bases other than positive a, so I'll just add here that a has to be bigger than 0 in all of these. Okay, rule number 1, if you understand rule 0, then rule number 1 should be easy. Log base a of 1 equals 0. Why is that? That's because 0 is the exponent you raise a to in order to get 1. A to the 0 is 1. That says that all log curves pass through the point x equals 0, y equals 1. I beg your pardon, x equals 1, y equals 0. Sure, all logarithms graphs pass through 1, 0. That's because all exponential graphs pass through the point 0, 1. And a log curve is just the reflection of the exponential curve across the line y equals x. It's the curve obtained from this one by just interchanging all the x's and y's. So log base a of 1 is 0. What about this one? Log base a of a equals 1. Why would that be true? Well, logarithm is the exponent you raise this to in order to get that. But this equals that. So sure, you raise this to the power 1 to get that. The log base a of a is 1. Property 2 comes from the definition too. Just look at this exponent. This may be a little bit hard to read. I meant to write a to the power of log base a of x. Well, log base a of x is the exponent I raise a to in order to get x. So what do you get if you raise a to that number? Well, you get x, because this is the exponent you raise a to in order to get x. So sure, when you raise a to that thing, you get x, just as promised. That can only be true if x is positive. You can't take logs of 0 or of negative numbers. So this bit stops us from using any x's other than x is bigger than 0. Also, it makes sense that x has to be positive, because if you're going to take a and raise it to anything, you can't possibly get a negative number or a 0. If a is some positive number, all its powers will be positive numbers. This one also, I think, is just the definition. If the number inside the log, well, log base a of a to the x equals x, it says. Why is that? Well, if the number inside the log is expressed as a power of a, then logarithm looks at that and says, you know, I recognize this as a power of a, and it tells us what the exponent is. But if this already is a power of a, I mean it's expressed as a power of a, the logarithm must be the exponent that I see right there. Okay, the last three I think are a little, not so much directly from the definition, they're a little trickier. Let's all go over them with you. Log base a of m times n is log base a of m plus log base a of n. In words, the logarithm of a product is the sum of the individual logarithms. So the logarithm of a product is the sum of the logs. So I bet you can guess if the log of a product is the sum of the logs, then the log of a quotient must be the difference of the logs. The log of m over n equals the log of m minus the log of n. And finally, if rule 6 says log base a of m to the t is t log base a of n, that is, if you're taking the logarithm of something which is a power, then that exponent gets to come down in front and the thing inside the log can be made simpler. These last three are all laws of exponents, kind of written from a different point of view, from the point of view of the exponent, I guess. Remember, log is exponent. I'm not going to try to give a complete proof of why these things are true, but I'll just sort of state why that's really a law of exponents rewritten in a different way. Remember, there's a law of exponents that says when you multiply two powers of a, the exponents add. So if m is a power of a and n is a power of a, then the exponent necessary to get n times m is the exponent necessary to get m plus the exponent necessary to get n. That is, when I multiply these two powers of a, the exponents add. When I divide powers of a, the exponents subtract. This one says that if m is a power of a and you raise it to a power, the exponents multiply. Let's try using those rules to solve some problems that all say simplify. So what about this one? 2 to the power log base 2 of 100. What's that? Am I supposed to know what log base 2 of 100 is? I hope not. But look, 2 to the log base 2, these two operations undo one another. By property 3 in the previous page, that's just 100. After all, log base 2 of 100 is the exponent I raised 2 to in order to get 100. So here I am raising 2 to that power. So sure, I get 100. How about this one? Log base 3 of 3 to the power 9.4, and I meant this to be like that. Am I supposed to know what 3 to the power 9.4 is? I have a hope of that. But look, this is a power of 3. So when I take its log base 3, logarithm looks at that thing and tells us what the exponent was. So this must be 9.4. Oh, that was easy. How about another one? What's ln? Oh, ln is log base e. So this is just the standard way of writing that. But now this is just like, this is enough like example 1. Look, it's like this exponential and logarithm operation, they undo one another, and I'm just left with a 7. That's what that rule 2 says. You know, the logarithm and the exponential are inverse functions. So when you feed the output of one into the other, it tells you your original input. Ah, they're getting a little trickier. There's 2 ways to do this problem. One is to recognize that the log of a difference, rather the difference of logarithms, is the log of the quotient. Like that thing up in the numerator is the natural log of 7 over 8. That's using property number 5 here. The difference of logs is the log of the quotient. So if this was 7 in number 3, this must be 7/8. E and the natural log function, they undo one another. So that's 7/8. I like it when there's more than one way to do a problem. So I'll kind of do it, that tells me like maybe twice as many students will get this one right. So here's another way to do this problem. You could say, when do I see a subtraction in the exponent? It's when one power of e is being divided by another. Right? E to the log 7 over log 8 would be the same thing as e to the log 7 minus log 8. So our guy is the same as that, thanks to one of the old laws of exponents. But now the numerator is 7 and the denominator is 8. That's why the answer is 7/8. Let's try another. This doesn't seem much different than the last one. The bases are 2 instead of e. So one way you could do it is you could remember that the log of a product is the sum of the logs. So when I see log base 2 of 5 plus log base 2 of 3, that's the same thing as the log base 2 of 15. Right, I'm using the fact that the log of a product is the sum of the logs. But now this is just e to the log, or rather 2 to the log base 2 of 15. The answer must be 15. That's a good answer. Or if you wanted to see it another way, you could say, look, when do I see addition in an exponent? It's when I multiply these guys. This one, say, times this one. But when you multiply 2 powers with the same base, in this case 2, the exponents add. So what I see there is the same as this product. But that's 5, and that's 3. Equals our 15 again. How about this one? Now there's no 2. I mean, this log base 2, they aren't being raised to some exponent. I've just got these log in them. Apparently I'm supposed to simplify these logs. I can calculate logs when I can recognize this number as a power of that number. But I don't see 100 as a power of 2. Nor do I know how to express 25 as a power of 2. I mean, it's not some integer power of 2. But look, the log of a quotient is the difference of the logs. What I'm supposed to recognize in this problem is that that's the same thing as the log of 100 over 25. And log of 100 over 25 is 4. Do you see it yet? Log base 2 looks at this number and says, what power of 2 are you? In case you don't see it, try rewriting it in exponential form. Say that's x. This would mean, if I can just squeeze it in here, that would mean that 2 to the x is 4. Ah, I know what that is. 2 to the x is 4. X has to be 2. Because 2 to the 2 is 4. So this log minus that log, I can't tell you what log base 2 of 100 is, not without a calculator, nor this, but the difference of their logs must be 2. I can squeeze one more in here. I'll try to do that. How about 3 to the power of 2 log base 3 of 5? We'll squeeze it right in here. If that 2 weren't there, I'd say the answer is 5. So one thing I can do is I can use good old Rule 6 that says a number in front of the log is the same as an exponent inside the log. That 2 can be brought up inside that logarithm. So this is 3 to the log base 3 of 5 squared. That's 3 to the log base 3 of 25. Now, this 3 and this log base 3, they undo one another. The answer is 25. Or, I guess you could have said, and this is where this rule number 6 comes from, you could have said, when do I see a multiplication up inside an exponent? It's when I've got 1 power of 3 raised to another power. The laws of exponents say that this power of 3 raised to a power is that power of 3. The exponents multiply. For that matter, I could have written them the other way too, but I think this is probably the more useful way, because what's the thing inside the parenthesis? 3 to the log base 3 of 5 is just 5. So that's 5 squared is 25. I'm glad to see we got the same answer both times.